Alright, greetings everyone. This is a presentation for the Temporal Distance Map, a warped isochrone map depicting accurate travel times. This was a project that originated at the Loyola University of Chicago and has since been transferred to the University of North Texas under the direction of Director Dr. Mark V. Albert, who was a director of research labs at both Loyola and the University of North Texas. So if you want to contact anyone about this project or what's going to happen in the future with the temporal distance map, be sure to contact Dr. Mark V. Albert at mark.albert@unt.edu. It's the email listed on the bottom of the slide. And so to give a brief overview of what we're going to be talking about in this presentation, essentially the temporal distance map is a tool that creates a visual representation of a map in which distance on the map, it represents travel time rather than physical distance. And so you can imagine in the age of routing applications, most people are more concerned with the time it takes to reach an area rather than its physical distance to the destination. And so things like mountains, rivers, physical boundaries, and public transportation, they have impacts on travel time that aren't readily apparent in a traditional map. And so we sought to create a tool that would morph these static maps to represent accurate travel times. And so to do so, we use travel data from the Big Maps API and a static image of a map. We would make a grid of points that represent both geographic and Euclidean points and use the metadata from the Big Maps API to shift the grid points on the map to accurately represent the travel times that we got from the metadata. And so with this approach, we can it shows a lot more information regarding the impact of barriers or access to public transportation, as well as physical barriers in travel time, and it allows the community to see their access to a surrounding region around them, and lets them understand what the area looks like in terms of travel time rather than its physical distance. And so for our presenters, I am Elijah Nacar, the presenter. I am one of the two undergraduate students. I and Devak Nanda created and brought the temporal distance map to life. And so we're both researchers currently at the Texas Academy of Math and Science at the University of North Texas, which is an academy at UNT for students who are around 15 to 18 years old. And so we will be moving on to college and are so junior in the research topic that for any other information regarding the temporal distance map, we would like to have you contact Dr. Mark V. Albert, who is the director of the UNT Biomedical AI Lab, which sponsored the temporal distance map and many other research endeavors. And so we have a brief introduction of Dr. Mark V. Albert. He essentially wants to use machine learning to automate and provide clinical analysis for like clinical research and just clinicians in general. And so you can find a lot of information about him in the Biomedical AI Lab page. And so this slide, we're just going to go over the Biomedical AI Lab. We have the link at the bottom, the biomedical/ai.com/home. And so on that main page, you'll find all this information that we're about to discuss and a lot more. And so the Biomedical AI Lab, it's a very busy lab directed by Dr. Mark V. Albert. As you'll see on the top left, we have 8 PhD students, 5 masters, 11 undergraduates, 1 affiliated lab, and 4 capstone groups for both the fall and spring 2020 semesters. And the mission statement of the Biomedical AI Lab aligns a lot with what Dr. Albert wants to do, where they use machine learning to advance medicine, historically making wearable device analytics to aid clinicians in the treatment of mobility disorders. And you can see some of the disorders we're trying to treat and some of our applications, as well as the machine learning techniques that we're using to do so. And you can find all this again at the homepage, where we'll have the links for both the Twitter, LinkedIn, and Facebook. And in the middle, we have a few of our projects. These are both just representative of those wearable device analytics that we're creating at the Biomedical AI Lab to aid clinicians in finding mobility disorders by prediction and validation of spasticity and remote human supervision in the home care robotic assistant prototype. And then on the right, just to show how busy we are, we have a tweet from the lab that showcases the 13 presentations that we're having in September and October. Yeah, we're a busy lab, and it's a lab that brought the temporal distance map to life. You can find all of our information on the Biomedical AI homepage. So introducing the temporal distance map, we have, or essentially placed with this idea of like the typical map. And so the typical map represents an area in terms of physical distance opposed to travel time. And so we were thinking, how do people sort of show travel time in maps? And most research and most people, if they want to kind of denote a map in terms of its travel time, use the isochrone map showcased on the right. And so this isochrone map is just basically showing the drive times around airports in northern Finland. And as you see, there's contours that depict like their little time restraints that are placed around the cities that showcase basically how long it will take you to reach certain areas away from the central point. And so that would be the major airports. And looking at this map, we have the contours that dictate the time, but it's a lot harder to figure out the actual relation of the travel time to the area surrounding it. And so what we want to do is we want to create a tool that would morph this static image that's showcased on the isochrone map and morph it in a way that actually moves the contours with the map so that the map showcases the actual travel time of an area opposed to its physical distance with the contours overlaid. Because the isochrone map depicts such a passive representation of travel time, we want to create something a lot more active that actually transformed the map to showcase its travel time. And so to do so, we utilized the Bing Maps API and used it to obtain both a static image of the location as well as the metadata for the points surrounding it. And so notice on the right we have a map of Chicago, and it's centered at the heart of Chicago with 961 points. And so each of these points are going to represent both a geographic coordinate, which is latitude and longitude, and a Euclidean point, which is essentially assuming this graph, say it is like the first quadrant of a rectangular graph. So the bottom left of the graph is going to be 0, 0, and the top right is going to be 1, 1. And each of these points correspond to both a geographic coordinate and a Euclidean point, and we're going to use that information to shift the map. So essentially we find the travel time between the center point and each of the geographic coordinates that correspond to Euclidean point, and then we shift those geographic coordinates with an affine transformation. We shift them radially, basically. We use the same radius but change their actual distance across, and by doing so, we create this transformation where the points are starting to align with their travel time. And so once the geographic coordinates have been shifted, we transform the Euclidean points that correspond to the pixels on the actual map, and that will create a transformation. And so you'll see in the image below, we have the contours, as you can see, like as if it was an isochrone map. Those are the gray lines that are going across the image. And those are going to represent 15-minute intervals from the central point. And so as we shift the geographic coordinates, you'll see the points, each of the points begin to move. We'll move the pixels that correspond to those geographic coordinates through the transformation of the Euclidean points, and we'll normalize those to the point that the contours are concentric circles around the central point. And so looking at the map on the left, you'll see that that's just like your standard map with the points overlaid, and then on the right, it's when we actually transform the map so that it has travel time instead of its physical distance represented accurately. And so at this point, we're just going to go over some of the utility of the Temporal Distance Map tool by going over how it shifts certain areas, generally around the US, but as we said, you just use the Bing Maps API so it can be used in any area. So essentially how the tool works is we insert a geographic coordinate, and so that can be whatever it may be. For this specific representation, it's going to be Pensport, Pennsylvania, which is right around the heart of Philadelphia on the Delaware River across from New Jersey. And so the point of interest on this map is going to be the Delaware River. And so if you're at Pensport, which is represented by the red circle on the left side of the image, if you were to want to get to any point in New Jersey across from Philadelphia, you're going to have to take one of the major bridges. And obviously Pensport is not directly in front of a major bridge, and so you'll notice that in the very center of the image, it begins to expand because if you're immediately at Pensport and you want to get somewhere in 15 minutes, it's going to be limited by the bridges across from you. And so that's why the parts on the right are a lot harder to get to than the parts on the left, aka the parts in New Jersey are a lot more difficult to reach than the parts in Philadelphia, because you're going to have to take that Delaware River. And so this is just kind of a representation of how a physical boundary is affecting the travel time within an area, and it's not readily apparent that you're going to have this constraint of your travel time by just looking at the standard map. You need the temporal distance map to showcase to you that, okay, this river is getting much larger, so it's showcasing that it's going to take a much larger time to cross the river. Similarly, we have Miami Bay. And so Miami Bay is an area in which the heart of Miami is much easier to pass than, say, the areas surrounding it. Because on the right you have the Atlantic Ocean, and on the left you have the Everglades National Park and the Francis Wildlife Management Area. And so to begin with the Atlantic Ocean, you'll notice that our center point, or the red point, is the heart of Miami. And so if you were to want to travel to the bottom right of the ocean, or the bottom right of the Atlantic Ocean, or the bottom right of this map, I guess not necessarily the Atlantic Ocean, but the bottom right of this map, you're going to have to cross this thing called the Key Biscayne, and that's that landform that's right in front, and that's that landform that is southeast of the heart of Miami. And so basically this is just showcasing how the Bing Maps API works. While we may not know what exactly Bing Maps deems as the most efficient route from Miami to the bottom right part of this map, we do know that whatever that path is, it's going to take much longer than if we were to want to go to the northeast part of the map. And we can attribute most of that to being the Key Biscayne, because you'll either have to go around the Key Biscayne, like on a boat, or you'll have to go across the Key Biscayne on a road and then um, go leave at some point of departure at the Key Biscayne. And so that's just kind of showcasing how the Bing Maps API is working to create these travel times and creating this pathing that's morphing the overall image. And you'll notice that in the actual heart of Miami, it shrinks a lot because there is so much road infrastructure in Miami that allows people to travel, so that you can get places right next to the heart of Miami much faster than you would, say, in the wildlife preserve that is on the direct west of the heart of Miami. And so talking about the nature preserve, in a national park, there's not a whole lot of road infrastructure because there's a lot of just wildlife, of course, because it's a national park. And so the Bing Maps API, when figuring out how far or how long it will take to travel across that wildlife preserve, it's taking into account that there are very little roads in the wildlife preserve, and so it's going to expand, which is showcased on the temporal distance map, in terms of time, because people are generally going to have to be taking a traffic or a very clustered road because there's very little road in the actual nature preserve. And if they aren't taking the road, they're going to have to walk, which is going to just increase their time much more. And so, in conclusion, we're just showing that the Miami Bay is just an example of how the temporal distance map is calculating these times. And then finally, Kansas City. So our usual 15-minute contours that we showcase on these maps has actually been changed to 5, and we're just going to showcase kind of how infrastructure is affecting these areas. So Kansas City has highways going in and out of it from across the state, and you'll notice that, or well, let's just talk about highways. So we have a highway, and what the highway is meant to do is it's meant to lower the amount of time it takes to reach a general um, physical distance, I guess. So along a highway, it's going to take less time to travel more distance. And thus, on the temporal distance map, whenever it changes, you'll notice that the highways are beginning to curve to kind of fit that idea that it's taking less time to reach more area. So more area around the highway is going to take generally the same amount of time to reach. And so this is just kind of showcasing the utility of a highway and how it's impacting this travel time along Kansas City. And so we have a little transformation happening on the right side. We'll just sleep it. This is Denton, and so this is just the shift around Denton. You'll notice the highway is starting to move, just the general locations across the map beginning to change where they are based around their travel time. And so you'll notice that in this transformation, it's a lot more relevant to someone's personal experience because they're relating it based on travel time rather than its physical distance. Say I were to look at a map of Denton, like at the beginning of this transformation, and I wanted to travel to Aubrey, or I wanted to know the distance if I were to travel to Aubrey opposed to if I want to travel to Eagle Mountain. And so obviously those places, at a glance, they're about the same distance away, but once they transform, you see that Eagle Mountain is much further than Aubrey. And so this is more relevant to the actual travel time that's taken for an area, and it allows a comparison of these travel times at a glance. And as we saw in the previous results, it provides a bunch of additional insight into the impact of geographic and infrastructural features. Think of like the Key Biscayne or the national park, and even just the impact of highways. It's showcasing how these are affecting travel time in a way that a standard map just you can't do at a glance. And so finally, we have just a few references. This is nowhere like close to how many references we actually used, but these are just some things to, if you were to trace our path, these are some things to get you started on how we devised the temporal distance map and why we wanted to create something like this.